In today's video, we will be discussing Physics 251, Week 9, Video Explainer problem number 65. So for this problem, we are trying to figure out the distance between a supernova and our telescope. So to start this problem, let's go ahead and identify some of the givens. So here we have our 2-meter diameter telescope, which we will be using for surface area. We have our star's energy right here, which we will be using for energy. We have the power in watts, and we have our time in seconds. We also have the speed of light down here. So for this problem, I actually had to draw on some of my Physics 202 knowledge in order to solve it. I figured that for a lumosity problem like this, it would be best to be using intensity, and given the variables that we are given, I made the decision to solve using power and intensity relationships. So this isn't necessarily the work problems that we've been focusing on in week 9, but I figured since I've taken Physics 202 that I would be okay solving with intensity instead. So what we're going to do to start off this problem is draw a little picture. So we have our lens of our telescope here, we have our distance, and we have our star over here. So what we're going to do is we're going to use some of these relationships here that I've written out for intensity, power, and energy. So these are equations relating the intensity of usually light to power and surface area. And then this is just rewritten from the same equation here. And then we have our equation for energy, which is just our power absorbed times our time. So to start off this problem, we're going to go ahead and plug into the intensity equation. So here we have our power in watts, and we have the surface area of the light that is coming off of the star. So this is pretty much the radius would be our distance, as the light is traveling in all directions from the star. So we would use this d value here, and this would also be the d value of our actual distance to the lens of the telescope. So from here, we can plug into the power absorbed equation here, and we're going to be multiplying this by the surface area of our mirror here, which is 2 meters in diameter. So what we're going to have to do is divide it by 2, leaving us with 1. And when we do this, our 4 pi will cancel in both of these locations, and the square of 1 is 1. So we are left with this for the power absorbed. From here, we can plug into our energy equation, and we're going to be setting it equal to our energy in the problem here, this 9.1, and our time here, time is 10 seconds. So after a little bit of rearranging that I didn't feel like writing out using the mouse, I got that the distance is equal to this right here, and it's the square of our distance, so that's why it's square root right here. So from here, this is the value that I got in distance, but notice it's in meters, so we need to convert it to light years. So using our equation for the speed of light, we can multiply the speed of light by the days in a year, by hours in a day, and seconds in an hour. So this will give us this value right here, and this is the distance that light travels in 1 light year in meters. And from here we can divide our distance value divided by our distance of 1 light year, and we are left with 2.477 times 10 to the 8 light years. So this is the distance that the star is away from the lens of our telescope. I hope you found this video explainer helpful. Thank you for watching.